how can we optimize information retrieval systems? There are a few techniques that we'll discuss today. First, do we need that? Always like to bring some examples from real-world systems. For example, here, very nice systems, very nice example from, was it, Continental. Very basic things that don't work. Here, for example, the linguistic preprocessing, an adjective with an N at the end, and there is no result. But if you, what is it? Interestingly, here you don't find a result for the basic form, but for the modified form with the EN at the end. Pietorescitiv, you find something with pietorescitiven, but not with the basic form. Quite strange, right? Shouldn't happen. The stemming went somehow wrong for one of, well, a rather large company. Another example from the same website, druckempfindliche Membran. No results. And then, if you search on Google, you will find that there is, in fact, a document with druckempfindliche Membran on the website of Continental. And again, either it's a linguistic preprocessing problem or a general problem. We don't know. Simply, you cannot find it. Right? So, a lot of investment. Make a nice website, but then the search will not lead the user to this document, to this PDF document. So a lot of users won't find it, and investment is basically lost. Also, what do we have here? Probably special character problem here. Innovation in the Portuguese side here. Inovação, as you may know, there's a special character for the C here in Portuguese, and you don't find anything. Innovation should be a term that any company has something to offer, right? Could be due to special characters. Other issues here, name entity, finding Jose Aula, somebody who is not just any name, this is somebody who is on the board of the company, and you find some results, but we don't find the list of the board members here with this query, which is strange, right? A person that should be well known in the company, and you should be directed to this result. Anyway, so a lot of issues are here. Another issue, for example, Allianz also, big website, Reiseschutzversicherung. So insurance for traveling, something that people might look for, people might want to buy. And strangely enough, an insurance provider does not have any result for Reiseschutzversicherung. Why could that be the case? Of course, we don't know. There could be many issues, yeah?
Isn't Reiseschutzversicherung offered by not by them, but by the ones who book the hotel chart?
The travel agencies.
Yes.
This is, now there are different types of travel insurance. Something that is a travel health insurance. That's actually what I'm looking for. And there is a travel, what is that called? Reiserücktrittsversicherung. Don't even know the English name. If you cannot travel, you get reimbursed your money. Don't know the English term for that. Anyway.
So maybe the right term for that would be Auslandsversicherung.
Yeah, could be a problem of terminology, right? I'm looking for Reiseschutzversicherung. I think I know what I want. But indeed, and that's the issue, it's not Reiseversicherung, it's, where is it? Reiseschutz. Here we see that they actually offer something, but it's simply a different terminology. Reiseversicherung instead of Reiseschutzversicherung, what I termed, right? It's not such a bad term, Reiseschutzversicherung, is it, right? They should look for how do people call this, right, and add this to their index at least. So you can find it. Also, Reisekrankenversicherung maybe, right? Even if the is not a technical term, doesn't exist, somebody might query, and you'll be able to sell one more insurance. Okay, so there's a lot of need for improvement in today's search technology, and we'll briefly discuss these optimization methods. Important is relevance feedback, and query modification will focus on query expansion methods and fusion, also fusion. That's at least what we should cover today. Let's see if we even manage to get to diversity and query answering. What time do we have? Okay. Relevance feedback. A very important technique that is known to work extremely well. So if a system would offer that, it would really improve the quality of search. Usually the system knows very little about what you really want. Right? The average length of web queries is 2 point something, so 2 or 3 words, that's not very much. So that it would be better to give more information. I think I mentioned it before, right? Longer queries have a better chance of getting good results. So if you can think of more terms, just add them, and then hopefully you might get a better result. Now, relevance feedback is a bit similar. It also tells the user, please provide more information to the system. But it's troublesome to think of more terms. It takes time, typing effort, so people don't like to do that. They want to type as little as possible, least effort principle. Right? And I have to think of terms. What could I call this again? Right? I have to remember, come up with terms from my memory, not so convenient. And relevance feedback says, okay, it's okay to just add a few terms, but then once you see the result, please tell the system which ones are relevant and which ones are not. So you don't have to come up with new terms. You just say this was relevant, this is relevant, this is not relevant. Send this information back to the system. The system will say, aha, this was relevant, this was not relevant, this he didn't say anything about. What does he really want to? Right? What does he mean when he types these 2 terms? Wolf Niedersachsen, maybe, right? As we had so many times. And now he thinks these 2 documents are relevant. What is typical for these 2 documents? Let's find more documents that have also the initial query, but they also like the documents that are judged as relevant. So the system knows more about your need, about your information need, by you saying this is relevant, this is not relevant. So there is a loop. There are 2 iterations now. There can be more, right? There's no need to stop if you want to. Reformulation, formulation of a query. First time it's really a formulation. You view the results, and judgment, something that people do anyway. Right? You look at something, that's not good. Oh, this is nice. And this is a mental load that you'll carry anyway. Now just let the system know. Right? And you mark this. Maybe there needs to be some additional interaction methods, like a checkbox or something. Mark the relevant ones, and the system will be informed. Right. So this can give more information. Here the thing in the relevance feedback process in our well-known graph, well-known overview. We get results in our interface, we do relevant judgments, and this gives the system more information. In addition to the query, we now know, these 2 documents are also typical, and of course, what will we extract? We have example documents, and from that we can get further additional query terms. We say, in these 2 documents, term X and term Y are very frequent. More frequent than on average in a collection, and that maybe these are interesting for the user. So we add these terms to the query. We have the initial query. Now we add some terms that we extract from the relevant documents. We get a longer query and send it again to the system for the second iteration. So the distribution of terms in relevant and non-relevant documents is, of course, the real information for the system. Add terms that appear in relevant documents, maybe exclude terms that are in the non-relevant documents. This is optional, right? More important is, of course, the relevant ones. Typically, relevance feedback leads to better results, but unfortunately, almost no system really offers relevance feedback. Why? Because users just don't like to do it. It's again another interaction step. Once people have their results, they want to look at them. They don't want to go through a second iteration loop. Unfortunately, right? It would lead, it's well known that this would give much better results. So obviously, even such a small burden of interaction is not accepted by most users. And that is why system developers came up with the idea of doing blind relevance feedback. What is blind relevance feedback? It's the same thing, just without real user information. We do an iteration, we get a result set. Now we could show it to the user and say, let's stop. No, let's assume we have relevance information, and we assume now the first 10 documents are just as relevant. And this we give back to the system, and then after the relevance feedback we get a second result with a new query, and this is presented to the user. So automatically we extend the query, we expand the query, this is called, we get more terms without asking the user really, because he's not going to do it. And that way we might also improve our system. Blind or pseudo relevance feedback, as I said, no user interaction. The system just assumes the top n, 10, 20, 30 hits are relevant and extracts some 10, 5 or whatever terms from that and adds them to the query. Okay. Just the illustration of searching, and this, I think, ends the relevance feedback information. Questions on relevance feedback? Not yet. Okay, so relevance feedback is just one technique within a family of techniques that are all called query expansion. The goal is always to give more information to the system, to have more query terms than the user types, because we know more information is typically better. So we have a very short query, we try to get different terms that hopefully are useful for this user intent. So we have user-based modification, relevance feedback, but we can also have query modifications without user involvement. Something that can happen to blind relevance feedback, as we've discussed, but there are different ways to also do that. Knowledge-based involve a thesaurus. We've talked about thesauri in the second class, I think, on manual indexing. Remember, thesaurus is a collection of terms with their logical and semantic relations. And we could do it automatically. We'll discuss that in a second. All these things I can do again with and without user involvement. I could say, I have a thesaurus, let's suggest something. And I can either automatically include that or first show it to the user and say, hey, do you really want this term to be included or not? So suggest, let the user select the expansion terms or not, right? This is optional. User involved or not. Here he is involved. And now we have these two methods. Let's discuss these two methods, knowledge-based and automatic expansion of similar terms that have something to do with the query and might be useful. Here first we have an interpretation of the relevance feedback. Oh, a bit too late now. In the vector space model. Basically, we could say that relevance feedback means moving the query more towards the relevant results. Let's assume these parses are documents that were judged as relevant. These are irrelevant documents. And this is my initial query. And saying, aha, this is relevant, this is relevant, this is relevant. The new query should be pushed closer towards the relevant documents. But it's still close to my original query, but closer to my relevant documents and further away from the irrelevant ones. Okay, this is a graphical interpretation of the relevance feedback technology. And remember, again, relevance feedback was something that we already discussed in the context of our network model of the spreading activation model. And remember, there we didn't have to think of it as a new technique. There it was inherently involved in the network functions of the spreading activation model. Right? I can inject interest at any point, it spreads out, and I can do it at any time, even after first iteration, after second iteration, whatever. It's inherent. So, second class of models, there you can look this up if you've forgotten about it. What do I use for relevance feedback? Well, we've discussed that. How many documents do I check? How many terms do I check? Which terms do I select? And there are very simple models like the Rocchio formula that would say, my new query 1 is the old query plus all terms from the relevant document with their weights minus all those that are irrelevant. So we simply add the term vectors of the relevant documents and subtract the ones from the irrelevant ones. That's a rather simple technology. There are other ways to do that, but we don't have to really go into this in detail. Also something you should be able to explain what relevance feedback is, but you don't have to know the formulas for the exam, right? What is term expansion now? Knowledge-based term expansion based on a thesaurus. Here is an example. Of course, we had different. Remember which thesaurus? Here we say already. Okay. Remember the thesaurus, the original function of the thesaurus, as we discussed it in manual indexing, was consistent indexing among a group of people. Right? Telling, we don't call it car, we call it vehicle, or we call it automobile. So, in case somebody wants to enter car in the library, for example, the system should then say, oh, no, you can't enter car. We all agree that it's called automobile. And then, also if the user searches for car, we can also direct him to the preferred term. That would be a very simple. More interesting are, of course, synonyms, related terms, broader and narrower terms. Synonyms, I can expand a query with synonyms. I say, the user typed this word, but there are additional words that I know mean the same thing, like car, example car. I also know that automobile is more or less the same, and vehicle. Let's add this to the query, maybe without letting the user know, and hopefully then he will get better results. Similar things happen also at Google sometimes. I could also do that only in case where I don't find anything, right? If I have a 0 result set, I could say, should I tell the user really that he didn't find anything? How can I help him, right? Let's add some synonyms. Or, if I don't find anything with synonyms, use related terms or even broader and narrower terms. I don't find anything with bank. Okay, let's give him something with financial institutions. And there are many thesauri. I think I put some on the LearnWeb also. Interesting results, for example, different thesauri call things differently. We had the example of car, vehicle, for example, Staatsquote, Staatsanteil. Different thesauri use this thesaurus from the social sciences in Germany. Says this is a synonym, but we prefer Staatsanteil, no, Staatsquote. Staatsquote is the preferred term, and if somebody queries with Staatsanteil, he should be directed to Staatsquote, and the same thing, of course, for the indexer. Okay? Again, looking at the spreading activation networks, something that happens automatically there. Remember that we enter a query in the spreading activation, spreading interest spreads out to the network, to the document layer, spreads back, and all of a sudden different terms were activated and were also active. And those were the related terms that are similar. Okay, the next step now, we don't have a thesaurus. We want to find related terms automatically, independent of queries. How can we detect related terms? When are two terms similar in terms of information retrieval? Any ideas? Any suggestions?
Not quite sure, maybe by using anagrams?
Yes, that would be a possibility. No? I can say, I will find similar terms that look similar, that also have similar words, right? Like, but I will have a hard time of finding something like car and automobile, or vehicle and automobile, right? Because they are spelled completely different. I can find things like, what would be example here?
Maybe from the results that before were clicked.
Before?
Maybe the results that people clicked before, like people who typed automobile in and people who typed car in, and then the results.
So considering the query, the click logs, considering what people accepted as a kind of a search result or viewed as a result, right? That is possible to assume that clicking and viewing a result is some sort of relevance, and then we have some relevance information, then we can use this. We can use this exactly in the same way as a relevance feedback, as a long-term relevance feedback that we use for future interactions. Generally, also adding this, be aware that relevance feedback is a one-session approach as we presented it. Right? The next user gets something, will not profit from the relevance feedback before. There is a different approach in the query logs that probably some search engines use. Yes, but possible. But we don't talk about it. We talk about much more simple things. But it's definitely a valid approach. How can I detect that a term is similar to another one?
Maybe I create a list where I put them. The one and the related one.
Yes, that is almost like a thesaurus. A very simple form of thesaurus, right? But how do I find the relevant, the similar? So I have a word bank. The user entered bank. Now I want to find related terms to expand the query. It's not so much, I want to expand that. And then I can have a list, I can have a thesaurus, but how do I get it? Either manual work, a lot of cognitive work goes into a thesaurus, but we want to do it automatically. Yeah?
Maybe by checking the most frequent terms from the top score documents, and then we could see that documents which have the term bank in it would most likely have something like money or something different.
Yes, that's possible. How is that called?
Something.
We have learned it today. It's exactly a good description.
I know you already mentioned it.
Blind relevance feedback.
Yeah.
Pseudo relevance feedback. perfect description of pseudo-relevancy. Is a possible way to find similar terms once I enter the query. Right? Very good. But then, of course, if the match is not good and things like that, there is a more general approach. Think of the simple, basic data structure that we have. What was that? What describes our collection after indexing? Document term matrix, right? We have a value for each term, for each document, that describes its importance. Like this. And how can we find similar terms looking at a simple document term matrix? So far what we do with the document term matrix is that we add another document which we call query, which maybe has 1 here because the user types bank. And then we compare this query to all the documents. So we calculate similarities between these objects. And what can we also do with this matrix? Of course, we could have revolutionary ideas. Instead of looking at the lines, we could look at the columns. Right? We can calculate the similarity between these lines. Think of all the similarity metrics that we've studied. Right? I can say how similar is house to bank. And that means if these two terms, like in this case, I compare these two columns, I say, both have a high median value. That's good for the similarity. Again, good for the similarity. How high? Oh, here it's quite different. That's not good for the similarity. Just like when we have calculate the hit value, the RSV, right, for between document and query. Low, high, they are not similar in this document. And that means I check whether the terms are similar based on their appearance in documents. Terms are similar if they appear in similar documents, document contexts. If they appear in the completely same documents, they have a higher chance of being similar. They won't have exactly the same values, right, because of differences, but if they appear in completely different contexts and never are together in the same documents, then we assume these terms are quite different. That's a very mathematical way to look at semantics, right? We don't know anything about the words, we just assume that. And that means associations, we call this association relations. Objects, once experienced together, tend to become associated in the imagination, so when any one of them is thought of, the others are likely to be thought of also. Principles of psychology, we remember things by associating them, even if they don't have anything to do with each other, objectively, right? And in retrieval, in a mathematical way, we think of associations of co-occurrence, occurrence of terms together in documents. Association, associative rules is a term, something that you know from e-commerce, that things are bought by similar users. This is also an association that the system uses to recommend things to you. And here, also something we can have in Google. I don't know if it's activated at the current version, but in previous version, we could look for something like similar pages, and that the system did exactly calculated this between lines, and now we look at the columns. So we can have the exactly same similarity matrix applied to columns, and that means we can have a similarity matrix between all the terms of the that means frequent joint occurrence means similarity. So we don't have to know what these words really mean. In this case, we can easily, of course, say yes, there is a bank has a high similarity with this word and also with this word, but these two have completely are completely dissimilar. They represent the two contexts in which bank can occur. One is the park bench, the furniture, and one is the financial institution bank. And these contexts are probably exclusive, right? We have some similarity between bank and all of those documents, but little similarity between these. Understood? Clear? Okay. So here we have the calculation, and now we end up with a similarity value, similarity matrix between all the terms. In this case, it's not normalized, so we have values that are higher than 1 because we have a very simple similarity metric, just the overlap in a product, but that doesn't matter. And we see that bank has a high similarity to money, park, and bank, but park and house and money and house have a, what is that, money and park have a low similarity, for example, right? Financial institution, reading, and furniture. Yeah, please.
Excuse me, I just wanted to know if I understood right. So you said that terms are similar if they have been in similar documents, is that right?
In the same documents, in similar document contexts. Right?
Context, okay.
So if there are like 1,000 documents, and there is a term that appears in 100, and there is another term that appears in 90 of those, and in 5 others, then they have a very similar co-occurrence pattern, right? They have 90% of their documents are identical, plus 5 that only one has and 5 that the other has. So they have a higher similarity. If each appears in 100 documents, 2 terms, and they have an overlap of only 1, for example, then they have a low similarity. Right? So just where they appear, a mathematical score, again, appearance of documents determines the association value, the similarity value between terms, between words, basically. Okay? Further questions? Please. Mm-hmm.
But how come that money actually has a higher similarity to house and bank than to money itself?
Mm-hmm. Ah, yeah. That's an artifact of the inner product. The inner product is simply the sum of the products without any normalization, like in cosine. And I use it because we could calculate it here on the board easily, right? But for time reasons. And since it's not normalized, it has these artifacts. If we would use cosine, we would spend more time on the board, but we don't have that. And then we have a normalized. For a normalized similarity metric, we would, of course, expect that all the diagonal values have a value of 1. And the inner product doesn't fulfill this criterion. So, good question. Hopefully resolved, because we use such a simple metric here, so we could explain it, if there are further questions. Further questions? Not the case. Okay, we move on. So, these statistical associations, they could even look useless for humans or be senseless. Right? Meaning, basically, when we see the word meaning of a term, we think of semantics and we associate some meaning with it. I have maybe an image of what something means, but here we just calculate the context of the word, the documents in which it appears. And this is very close to what the language philosopher Wittgenstein says. The meaning of a word, it's its use in language. This is exactly, basically what we do here. The use is the distribution over documents. That's what we use for the meaning of a word, to calculate similarities. We don't know anything about the meaning of the real, what we as humans would call meaning, right? Okay. That is so much to term expansion. Then, of course, I could look at the similar words and add them to the query, right? So for term expansion, we have relevance feedback, involves the user. Pseudo-relevance feedback does not involve the user. We have expansion used based on knowledge in the thesaurus, or on the knowledge that we extract from the collection by calculating similarities. All that is term expansion, query expansion, adding more terms to the query, because then we have more chance of being successful. Okay? Any questions? If not, we move on to the next topic for optimization, and that is fusion. Fusion also music style, isn't it? But it has nothing to do with music here. Fusion is closely related to meta search. It's also called rank aggregation, but it's a bit different from meta search. We already talked about one fusion method. Fusion means we have different ranking algorithms, different indicators of relevance from different sources maybe, and we want to bring them together, right? We want to have several evidences and fuse them. This can similar in meta search engines or even multilingual retrieval, but what our things that we fuse, our indicators or evidence comes from different ranking algorithms. And we had one case already where we did basically bring together two elements, and that was when we talked about link analysis. We said we have per page rank value and we have a normal similarity value. We have to bring them together to come up with one final result for a web page. Okay, and we simply did that by adding them, I think, in the class on web retrieval, or multiply them. What did we do? I don't remember well. I think we added them. Now we will see that there are different ways to bring results together, very simple ones. Why do we do fusion? We've already seen this image, I think, and we know that, there are some, this is a very typical result. We know that there are quite good systems, and best systems, they are quite similar. Their performance is quite similar. We can almost tell no difference between the quality of these systems. Their MAP values are very close together. Probably between 2 and 3 there's not even a meaningful difference, a statistically significant difference. And we are faced with a situation where we have to select one of these algorithms. And looking close into these algorithms will show that, yes, on average, they're very similar in their performance. But system A might find different relevance documents than system B. And that is very typical. So we could simplify and we could say that, yes, different algorithms find different hits, but overall they have the same quality, right? So the idea would be to bring them together and then have a chance to find relevant documents at A and relevant documents at B, only B finds, right? And bring them into one joint list. And that's why we fusion algorithms are positive. Here it's again the text for that. And this is related to so-called committee machines, typical algorithms where several algorithms work together, like in machine learning. We have different experts. The metaphor is an expert meeting, right, where different people come together, bring their opinion, and then hopefully the committee comes up with a better decision than any individual. And that is what we try for algorithms in AI and machine learning. It's called committee machines. For information retrieval, we call it fusion, or sometimes rank aggregation. Also in web retrieval, fusion is also popular. So-called meta search engines, where you can query several search engines or once. But there is a different reason behind that. The reason there is that each individual search engine has a low coverage, that is around 50 to 30% of the web, which is a very constant value, even in the growth of the web. And there the idea is if we query several search engines, we get a higher coverage. Right? In Fusion, the idea is different. We have an RSV for each algorithm gives me an estimate for each document, and I want to get higher quality, not higher coverage. For example, very simple, I have 3 results from 3 algorithms. You know how we can create different algorithms, right? Different logs and different whatever. And here we have a situation, if algorithm A says, or 1 says, this is the top score document, A, with this value, retrieval status value. He says, oh no, it's B. B is with 0.9, must be the best one. And algorithm 3 would say, no. A is best, but only with this value. So now I have 3 experts, or 3 algorithms giving their vote. But I want to bring this knowledge together in one ranked list for the user. What would be the top document in this case? What do you think? How can we calculate one list from 3 or more lists? What is the number 1 hit? Of course, there is no perfect solution. There are many solutions now. But what is your initial feeling? Is it A? Is it B? Is it C?
Maybe C, but I can't explain.
C?
Yes. C is not a top document in any of the 3 algorithms. No, I understood wrong.
Okay.
I thought the whole column. I thought you meant this one is A, the other one is B and D, and the other one is C.
Okay, it's a misunderstanding then. Okay, that's. But any other solutions? Anybody else thinks C is a good hit? Who thinks A is a good hit? No? Who thinks B is a good hit? Okay, B is popular. Why? Must be because of its high retrieval status value. If I sum up all the RSVs, actually that's what we learned in the web retrieval case for aggregating retrieval status value plus PageRank. So it's a good idea, show that you paid attention. I end up with 0.45 plus 9 plus 6, 1.5, quite a high number. If I do the same for A, I will get a much lower number, 0.9. Okay, good idea. What about the advocates of A? What could be reasons for them to challenge this? A is much better.
It has a top position twice. And
Yeah.
the only ones.
This is, I could simply count the top positions. So, but 2 algorithms think it's the best, right? What do you want with B? It's only once. Other reasons?
Same reason.
Same reason? Okay. Other reasons for B? For A. Well,
If I calculate only differences, or normalize the counting, maybe then I can sum up better.
yeah. how can I compare this first hit that only is 0.5, right, to this one with 0.9? The numbers that don't mean anything to me, really. They are only meaningful in comparison. So I would have to normalize these lists and say, aha, this is the top, so it gets the highest score. The highest score is different in these two cases, but I cannot compare really these algorithms. So I would have to normalize these lists, and then I can check, and then probably, maybe I did it, let's see, maybe the next slide, I would end up with higher values for A. Because if I normalize, this is 1, and this is 1, right? So I end up with a higher value for exactly. Other arguments? I could also check what is the minimum value. Right? Maybe A would have, in this case, the minimum value is identical. Right? I don't have an indicator. I could also check what is the lowest position. And say, aha, A is on 4. No, B is always, at least at position 3. So there are lots of different ways to do this now, of course. Let's check some of the, I could also filter something, and transparent fusion as a filter or upgrade, but basically what we really want is to make, how can we make one ranking from several lists? Several different ways. Very simple is the round robin approach. You simply take one from each hit at a time. If it's already in the list, then don't do anything. Then what we did was a sum now. Automatically people summed up, right? Sum of RSVs. And you said you should normalize first. We could also take the minimum or maximum. We could take votes. How many votes are there for top position for A, B, C, D? And also popular would be a multiplication. If I multiply, then low values will give a higher impact. Right? If I have a 0, if some algorithm says, or expert says, this is really not relevant, then I can't win at all, right? I'm out if I have a 0 value in multiplication. For adding up, it doesn't matter so much. If the other think I'm really good, it's a really good document, it still has a chance to get there. So, different methods. Here is an example for normalization. We have two lists. I normalize them, so we have a 1 and a 0, 1 on top, 0 at the bottom. And then we can do the, we can sum up the values and compare. Okay? So quite easy. If you know which function to use, you can simply do fusion. Questions? And we are, in this case, just to show, of course, the fusion method has an effect. I use the minimum and here the sum. What else? Normalized sum, maybe. Round robin, max, and normalized sum. We have two initial searches, and here we have 5 different methods for fusion, and we see sometimes A wins, sometimes it doesn't. Now we can think which one is the best result, but we won't do it here. You should be aware that, you should know that, of course, different fusion functions can end up in different ranked lists. Okay, we don't have to go through the list in detail. Yes, please?
I didn't really get the round robin in this example.
Round robin says, take one at a time. So start somewhere. In this case, we started with this one. Okay, the first one is A. The second one will be from this list, B. The third will be again from this list. C, B we already got, so forget about it. Take the next one, C. C, we already got it, so take D.
Okay.
Take one from each basket at a time.
We have F.
F. Yeah. Sure, good point. Round robin should also have F, yes. Forgot it. Yeah, but I mean, each In each fused method, we only have 5 hits are allowed. Okay, I forgot to say that. No, F would not be in the list. We have 6, no 5. 1, 2, 3, 4, 5. 4, 5. All of them are 5. F should be there, it's true. Isn't. Good point. Further questions? Anything that you cannot understand or say, aha, how does it work? How does it? We come to this. Yes, please.
I'm sorry about
No problem.
the example for the sum. Why is A 1.4 again?
Let's check. Oh, wrong. Good point. A is actually 5 plus 5. So 1.05. Forget this. And B is also wrong. 1.35. So we should switch these positions. Good question. Is at least C? C is also wrong. Wow. Let's forget this slide. Too much confusion. But basically, you know how to calculate sums and multiply and minimum maximum, right? Very straightforward. Further questions? Fusion can also be a linear combination where we give a value to each algorithm and say, this is a good algorithm, this is not such a good algorithm. And by time, these weights could change, and we could have different scoring methods, more advanced scoring methods than simply doing sum and stuff, but for our terms, that is okay. Interestingly, there are also systems that actually do fused search or meta search, for example, AfterVote. I think it's not online anymore, but it was quite a nice system that you could search, and it searched 3 algorithms and gave you an aggregated result and even told you this is the first result at Yahoo and the first result at Bing, and this is the first result at Google, and my ranking is like this, and this is the first result, third result of Google, and so forth. And then you could say, oh, that's nice, but I like this better. This should be on top. Then it would say, aha. Then you trust more the Google ranking, and you would upvote this and say, aha, for me Google has a higher relevance, and with over time, Google ranking has a higher weight within the fusion process. AfterVote, because your vote would vote this thing. Unfortunately, I don't think it's online anymore. The other, here, vote up, there we say. We could say, this is more important for me, next time this should be on top. This is something like you said, the click definition, right? But from a different perspective. So, Fusion can improve results even if one of the potential systems is not such a good contributor, and Fusion has a high potential when the single systems are very different. For example, I combine a Ngram approach with a word-based approach, or I combine completely different ranking algorithms. Right? Then there is some potential in the Fusion. Questions on Fusion? Not the case of query expansion, we have Fusion. Then we jump over result set diversity, and we come to, as a last topic, to question answering. Question answering. Question answering advocate said yes. Information retrieval sounds quite interesting, but basically what most people do is only document retrieval. You end up with a document list as a result, and you don't end up with real information. Then you have to read the document and find the information yourself. Why not present allow the user to ask a question to specify a real natural language question as a query, and don't give him a document, but find the result for him, extract it, and give him the fact as an answer. Frage-Antwort-System in German since the 1980s. There has been research on this topic. So give him the basic idea is to do retrieval and then extract a small portion, maybe a sentence, maybe a word from the document that is the answer to the question. Not the query, the question, right? So here we find a document and then we extract the correct part that the user wants to know and present it to the user. So what the challenge that QA systems have is they have to determine what kind of information it is queried. For example, if the query goes like, where is something, then I have to know, where, that means I have to find a place name. Probably the answer must be a place name. I have to use natural named entity recognition tools to find where are their names and which ones are place names, extract them and find the correct one. And of course that's not so trivial. We have to know, we have to have an answer type taxonomy, what happens if I query where, what happens if I query who, and we have to be able to not only do indexing and retrieval, but also to extract the correct sentence and the exact answer. So in addition to the standard technology that we need for retrieval, we need to identify textual information, recognize NDRs, and extract the real semantic information. Okay, we can quickly jump over this. For example, question taxonomies, we have different things. These are examples for question. In which city Emil Fischer was Emil Fischer born? And then we have, or how many inhabitants has a place? Then we know, the answer should be a number. All I need is a number, I don't need a document. And, these things can be quite effective. Some systems reach between 20 and 60%, and interactive systems this can be even higher. Okay, we have here, for example, a result system, in this case cross-lingual, goes from English and looks for German answers. Here the answer for the question was, who is Minister for Environment in Saxony-Anhalt? And it's not yet perfect, as we see. There is a sentence has been extracted, not only the real named entity. Also here we have systems on the web that you can use and look at, Lexicom for example, where you can type your query. What is information retrieval? Question mark, a full sentence, full natural sentence question, and then you get some explanations. Let's see if we have other systems. A question here, what is the size of the new iPod? And then I get some answers, plus their supporting documents. Where is this answer contained? The first answer might be correct, 0.4 inch. The next answer, 1/10, doesn't really help me a lot. And then there are even worse answers. Okay, but this technology is out there on the web. Another system, Start system, that's still online. Again here, when was Wittgenstein born? I can query, and it gives me a result with the source Wikipedia, the source Gutenberg, and you will see, here on Wikipedia it gives me a real date, whereas for this source it can only extract a year. But at least in this case they don't contradict themselves. Again, here you get another result, same actually. And then if I have 3 sources giving the same answer, it might be true, right? So try these things. Scour is also a system that you can use. There is another homework, even if you still need to do a homework to be able to take part in the exam. You can do it until tomorrow. and submit it online. So that basically concludes what we have to talk about today. Are there any further questions on the exam or on